Okay, welcome everyone to Cal 2, all right? How you doing, Rob? Good. Let me just make sure that no one's standing out there at the other classroom. All right, so my name is Robert, and I'll be the instructor for this summer class. I'm going to try and make it a permanent move to this room, only because I have two classes today, and I want them both here so I don't have to like redo all of this somewhere else. So it's not official yet, but that's what I'm going to try for. Okay. I'll put a note on the other classroom next time. Assume it's going to be here though. All right. Let's start off with some administrative stuff. I have a folder here that I'm going to try to remember to pass around every day. I'm not real good on remembering this. This is attendance. All right. So I'm required to keep attendance. If it were my opinion, my choice, I wouldn't. But I have to have a record of when you were here, when you weren't here. That way, if you fail or something like that, I can say, okay, look, they weren't here and they stopped showing up, and so I have something to go off of. Okay, so please, just when this comes around, find your name, initial underneath in the correct column, and pass it around. All right. So if your name's not on here, just talk to me after class. I know there are quite a few of you who are just here for the summer, meaning you probably go somewhere else to school and you're just here to knock out a class during summer and get back to wherever you are. What I'd like to do is start off with like a polling, like just ask you some questions. Before we actually get to the syllabus, we're gonna do some polling, and to do this, I'm using these little clickers. Now, if you've had me before, I used to know who you were. We're going to go completely anonymous here. That way you can respond freely. All right, so just take a clicker. I'm put a few on each desk. See if these work. I haven't checked the batteries on these in case some other people show up. I just want to get to know a little bit about you, and so you can kind of see who's sitting next to you, what their interests are, what their goals are. So let's see if I can get this going. Let's see if this works. Okay, so I believe if you click on, there's options like 1A, 2B, 3C. Everyone just hit 1A. All right, so we have 16 responses so far. All right, now click 2B, see if it changes. So you can change your mind, okay? All right, so let me stop the polling here, and I'm gonna start it again, and I'm gonna ask questions. So how many of you are at a university outside of this college, and you're here for the summer taking a summer class? Yes? No? You can say no if you have been here or something. So we have what? About 2/3 of you, 70% or so, are just here for the summer taking a class. All right. Next question. How many of you have taken Cal 2 before? Yes or no? So I want to see how many people are repeating the class. For whatever reason, I'm not going to ask you why. All right, so we have a third of the students are retaking Cal 2. All right, that's not surprising. All right, let's get a little bit more information about your majors. How many of you are engineering? I know that's very general, but how many of you are engineering? Yes or no? Come on in. All right. How about if you're computer science, include yourself in there? What else am I forgetting? Math, and what I'm trying to do is figure out who these people are. Who's here that's not a major math-intensive major? So things like what is it? Pharmacy? No? Okay, did you have a question? No? Okay, that's all right. So anybody out of this 18% want to tell me what their major is? Don't be shy. No? No one from the 18? Yes. Okay, all right, that's math-based. Yes? Architecture? You need Cal 2 for it? Really? Wow, okay. Good. So, you know, I've been teaching college courses since like 2000, 2001, something like that. And it's amazing how much they've changed what the requirements are for certain degrees. Like if you used to want to get a biology degree, you could stop at stats, maybe pre-cal. That was it. Now you need Cal 2, right? So they've really upped, you know, anytime they want to weed out people, right? When they want to thin the herd, they just up the math requirement. That's all they do. So, okay, how many of you passed Cal 1 with an A? All right, so what, less than half, that's okay. How about with a B? Now our data is getting a little skewed. Let's start this over. If you already voted for A, don't put no, all right? So how many of you passed Cal 1 with a B? So about 5 people, right? And C would be the only thing left. So, all right, anything else y'all want to know about yourselves that I can ask the class? No? Okay, let's try this. How many of you are working this summer? Oh, wow, okay. That's surprising. How many of you are working over 20 hours a week this summer? I didn't mention, I'm recording all of this. That's why I'm not writing this down. I can go back and look at it, okay. What else? So how many of you feel like you have at least 10 hours per week outside of this class to commit to this class? 10 hours or more, yes or no? Okay. So I'm going to hold almost all of you to that now, you see? So you can't say you didn't have enough time to keep up with the class. All right. That's probably the most important thing to ask in a class like this is how much time do you have outside of class? Because, you know, we can only do so much in here. Once you leave is where you're going to, you know, have to go and really learn this stuff. Especially if you're retaking Cal 2, you know that it's the repetition, it's the seeing it again, seeing a different version of it, seeing another version of it, and then finally kind of catching on where it's just almost instinctual. You're seeing it before you're doing the problem. So, okay, I think that's good. What I'll try and do is I think we'll just keep these clickers out for a while. I don't know how many days we'll have them out. I may just stop bringing them. And what I'd like to do is during class, you know, maybe just ask the class, you know, how is this? Do you understand? And you can tell me yes or no without actually having to raise your hand and embarrass yourself. All right. Not saying that that's what it would be, but some, you know, people are shy. They don't want to speak up. All right. So let's get to the administrative part of this. Since there are so many of you that are here for the summer and, you know, are maybe not familiar with Northwest Vista College, you know, there's pros and cons to a community college, right? I mean, one of the pros is that there's less than 20, I think there's 26 people in here, which makes it a little more intimate than being in a big old auditorium, you know, at a major university. You know, so I want to kind of look at it that way. Like, we want to try and form groups in here and work together to try and all succeed in the class. All right. So I don't know how much time we'll have to actually break into groups and practice during class, but this is a marathon of a course, like 9 to 12:30. It's a long class. I don't know who I was talking to a friend yesterday. I'm like, who can sit through a class from 9 to 12:30? Who does that to themselves? You know, you did. So I'm going to try and break it up a little bit. I'll do my best to, you know, let's just now you work a problem just to kind of break you off of just sitting there. But at the end of the day, Cal 2 is a lot of me introducing a topic, and so we don't have a lot of time for that sort of activity. But I'll do my best. I also would like to take a break, maybe about an hour, 40 minutes in, maybe about 10:40, 10:45. Take a little 5-10 minute break. Just everyone get up and walk around the hall or just stretch out, whatever. Y'all okay with that? Okay. I mean, we'll see. Sometimes I'll be like, you want to take a break, and everyone will be like, no, let's just keep going, and we'll just do that. But I do not expect you to sit here the entire time. So if you're not familiar, back to this, if you're not familiar with Northwest Vista's website, then this is it. You click on this tab, log into ACES, and come on. You log in, and if you don't have your login information, there's a little, I think there's a place here you can get it. Can you all see this okay? We just got new projectors. They're super bright, and I'm using 1600 by 900 resolution on this, and I think that's only 1280 by 720, so it's pretty high res, but there's a lot of information on screen. So if it gets to the point where you can't read what I'm putting up there, just let me know. All right, we'll change the resolution. So once you're here, you click on My Courses, and then you should look at Summer 2015. You should show what classes you're in. I'm teaching these courses this summer. 2 of them are online courses, and 2 of them are face-to-face. So the Cal 2 and the College Algebra are the ones I'm doing face-to-face. So you click on your Cal 2, and this is our main website. All right, this is where we go. This is where I communicate with you. If I want to send you a review, or you know, I say I'm going to send you a quiz tonight. This is where I'm going to send it. All right, so you come in here, and there's an inbox here. This is where you would find anything I send to you. But this is like the main page for our course. We have the syllabus. We have the schedule. We have the lecture videos, which is what I'm doing. Everything I'm recording now will be uploaded to YouTube later today, and you can go back and watch everything that I do. All right, so that's where you get to them. All right, and then files. I'll show you that in a second. Let's look at the syllabus. I'm going to go through this quickly because I know you can read, and this is Cal 2, so you've got some experience with college. It's not the first time you've ever seen a syllabus. Our official meeting times, that classroom thing will change. Did I introduce myself, Robert? Yes, I said Robert, right? Robert DiGiovanni. My office is way down at the basement of this building, basically. My intention is to, if I can get the official switch of rooms, is immediately after this class, go down to my office and eat lunch, 15 minutes. Come back up and be in here till 2 with no students. I mean, you're welcome to stay. So in other words, after class, if you want to stay in here and work on homework problems, go let me eat lunch and come back up here. I'll have a good, you know, till 2, so we get out at 12:30. So we'll have like hour and a half maybe to, you know, me answer questions. You can get up on the boards, you can do whatever. So this will be kind of like the official office of the summer, if I can get the change. They told me there's no classes in this room all summer, so I'm trying to take advantage of that. So even though it says my office is down there, this is where I plan on being after class. If you need to meet with me some other day, some other time, and I say come to my office, that's what I'm referring to. All right. My cell phone number is on here, so I already have had a few people call me on my cell phone. If you need to get in touch with me, that's the best way to reach me if it's urgent. All right. If it's something like I'm not going to be in class because I had a family emergency, you send me an email. And to do that, you go through that inbox I showed you, send an email to me. Just let me know, all right? Office hours, I just told you, I plan on being in here right after class until I have a class at 2 in here. So between that, when we end till 2, I plan on being here to help. The book you need for this class, I'm sure there's electronic versions of this. I'm sure that there's pirated versions of this. You know, it's the Essential Calculus by Stewart. Stewart's a very well-known author when it comes to calculus. This is like their, almost like a condensed version of calculus. I do not like this book. I've never liked it, but I don't make all the decisions in this department. So this is the book that we're using, all right? It's required that you have access to this book because I will assign homework from this book, and you need to be able to see what the homework problems are. So get that as soon as possible. You'll have homework tonight, so if you don't have a book, just, you know, maybe you can come snap a couple of pictures of the homework sets. I'm not going to do that every class, but, you know, just to get you going. Can we shut the door? All right, thank you. I forgot to do what I normally do in my class. We have to come up with a plan if there's someone going down the hallway trying to shoot everyone, like where we're going to go. And yeah, this is a good room. So these windows go out onto maybe a 8-foot drop here. Goes out to a little pavilion, like a cover patio, and then you probably run all the way out to the end, and you'd have to jump off. It's going to be about 15 feet. Might break an ankle, but the first couple of people would act as cushion for the rest of us, I guess. So that's a way out, just so we know. All right. Have y'all heard Texas legislature is trying to make it where you can carry on campus? Interesting. I don't know. We could get into, and we could spend the rest of the class talking about that, couldn't we? I think it's kind of weird because you can actually carry concealed all over campus. You just can't go into a building. So, yeah, anyway. All right, yeah, let's not go there. Now, the notes that I go through in this class, I have notes for most of the course already pre-made. I'm going to try and finish off the rest this summer. I post these online. I'll show you where they are. You could print these out, or if you have a laptop or a tablet, it's fine if you bring that and use that to view the notes. Right? I just don't want you on your laptop doing other things in class. So with the syllabus thing, you have to have the book, and if you want, you can have a laptop or tablet to view notes during class. Graphing calculator, optional. You really don't need a calculator really that much in this class. I mean, you need a scientific calculator. You need to be able to take square roots of things and, you know, things like that. But you don't need like the most, you know, high-tech color 3D graphing calculator out there. All right. So graphing calculator is optional. Prerequisites, objectives, outcomes, I'll let you read through that. Our grade is determined by quizzes, which will be 10% of your grade. You'll have an exam 1, which is, well, you have 3 exams and then a final. Each exam is 20%, the final's 30. Exam 1 will only cover material up to exam 1. Exam 2 will only cover material between exam 1 and exam 2. Exam 3 will only cover material between exam 2 and exam 3. The final will cover it all. All right, that's why it's worth more. Course policies. I do have some stuff in here that's important with the policies. Attendance, you need to be here. If you're not showing up, then you can be dropped from the class, or you can be failed. So if you just stop coming for like 4 days and then come back, then you actually are leaving your grade up to me. Because I can say, you know what, I can let you continue in the course if I want, or I can drop you, or I can just fail you for non-participation. So how many absences do you get in a class like this? 2. That's it. So in a summer course, you can miss twice, no questions asked, fine. Now if it's excused, then, you know, that's different, but, you know, you have to deal with explaining to me why it is you missed. Again, I'll let you read through what to expect in this class. Well, I've already talked about, I use a lot of technology, so everything's recorded. All the notes are provided online. That's an example of one of my recordings. Electronic devices. I'm highlighting that one because it's important. I'm not okay with you sitting on your phone during class. I'm not okay with it. And so for the entire time between 9 and 12:30, you are to disconnect from the grid. You are to not update your status on any social media. You are just to be in class. And so phones that are sitting on your desk, if you can keep them out of your hands, that's fine. But if you're messing with your phone, the result is a 10% penalty on your next exam. That means it's not possible for you to get an A on your next exam. That's a pretty harsh penalty, but that's my policy. They haven't told me I can't have that policy. That day will come where they will take that away from me. But this is not a place to be sitting here on your phone, all right? Also, sleeping. Do I have sleeping in here? Yes, sleeping or being disruptive. So if you're sleeping in class, again, 10 points, 10% off your next test. Again, that's hard because it's a long class. But if you're that tired where you're starting to feel yourself, you know, go in that place, stand up, go sleep on the bench out there. I don't care. Just don't do it in here. All right? Pack up and go. Just don't sleep here. Scholastic dishonesty, cheating, major consequences for cheating. I just don't go there. Tutoring. This is Cal 2, so the tutoring help is going to be limited. We do have some good tutors in the lab, but again, this is not a university, so we don't have math majors sitting over there that all have degrees in math that can help you. It's a little different. So if you need help, you need to reach out for help. You know, ask me. You have my cell phone number. Okay, it's up to you to ask for the help, though. The rest I'll let you read. All right, that's our syllabus. The schedule. So I have the schedule here so that you can print it out. Shows what we're going to do. It's kind of a day-by-day rundown. So today we're supposed to cover some stuff that you may have already seen in Cal 1, inverse trig functions and hyperbolic functions, specifically derivatives of those. And then we get into antiderivatives. So again, this is still stuff from Cal 1, a little overlap here. And then we get into substitution and then integration by parts. That chapter 6 is really where the Cal 2 begins. And then from there on, it's everything on exam 1 is integration, which is antiderivatives. If you've never heard of that, don't worry. Everything between exam 1 and exam 2 are applications of integration. And then everything after exam 2 to exam 3 is series. And there's some parametric and polar stuff in there. And then towards the end, we finish off with more more polar calculus. So that's it. Notice on the exam days, we take an exam, and after the exam, we continue. So what I'll do is the exam will be half the class, the first half. After the exam, if you're done early, you go wait in the hall, you eat something, whatever. After that half of the class is up, time's up, turn to the exams, then we continue lecturing because there's just too much material. We don't have time. Okay? Unless the class wants to vote and just do midterm final, 45%, 45%, 10% for quizzes. Y'all want that? No? A midterm that's 45%, but you get the whole class 9 to 12:30 on it? No? Okay, that's a lot of information. How many of you are in classes right now or have taken classes before that are like that, where you have midterm final, right? Yeah, that starts happening more and more as you move up higher in college. You start to have you know, 2 tests that mean everything, right? High stakes exams. All right, so we'll keep it like this. Lecture videos. When you click on this, it'll take you to my YouTube channel, and there's nothing in this playlist. But if you actually click on playlist, you can look at old classes that I've done. It'll say past. It'll say what is. So this is my Cal 1 from spring 2015, and you have to keep in mind these videos were not made to like be surfed by, you know, searched by people just out there trying to learn math. These are just for my students, all right, that semester. So but it's still something you can go back to and look at if you want. Understand? Yes. Right here. Yep. Just click on that and it'll go there. But if you don't want to go through all this, just go to YouTube and type in my name here. This is my YouTube channel, Robert Math Guy. Okay, just type that into Google. If you see this image come up in the search, you'll know you got to me. Okay, and then from there, click on playlist and go. All right. Files. Okay, so there's a lot of information here in files. All right. We've got the schedule, which shows the day by day what we're doing. Course notes. So like I said, I have pre-made notes that I use as I go through my lecture. I do not print these out for you and bring them to class, except today. So that's where they are, though. You can see 3.5, 3.6, 4.7, 5.5, 6.1, and then it kind of dies off after Chapter 6. And that's because it's hard to make notes for Chapter 7 and 8. I prefer to just do them as I go, like write them down. So I'm going to pass these around. The notes for 3.5, kind of the thicker stack here, and then I'll start the other one, 3.6. Just pass those around. Take one. So, but this is where you'll find them. So when you come to class next time, you should have the notes for what? What's our schedule? Where's our schedule? I don't have it anymore. Who has the sign-in sheet? Anyone have the sign-in? Where is it? Did that get around everyone? I have a printout of the schedule on the back of the sign-in sheet. So next class, we're supposed to do 4, 7, and 5.5. So you should either print these 2 out or bring a laptop or tablet so you can follow along in class. All right? You make sure you're prepared for next class. Understand? Okay, that was the class notes. Formula sheets. You are allowed to have these formulas on all of your tests. But these are the only things you're allowed to have unless I tell you you can have something else. So you can't be like, hey, I have this formula sheet that I was using in my Cal 1 class. I love this sheet. This is my baby. Can I use this on the test? I won't allow it. Everyone has to have the same thing. All right? So this is what you're allowed to have. So my suggestion would be to go through this 6 pages and know where things are, become acquainted with it. All right? It has a lot on here. Lots of derivatives, lots of antiderivatives. Same one. Yep. If you took Cal 1 with me, it's the same thing. Then I have old exams and solutions. I have just a bunch of old tests up here. Some of them have solutions. Some of them have errors. I mean, it's just a database of old stuff. So it's not organized in any, well, a little organized, but there's stuff that can be confusing, but it's not intended to be, you know, like this free ride of here you go, here are all my tests now you're ready. It's just, there you go. That gives you an idea of things I asked. There's also homework solutions in here, though. I have solutions to certain sections. Let's see. Let's bring one of these up. I don't see anything from Chapter 5. What's our first section here? 3.5. I don't see 3 here. Do you? I don't see chapter. I don't see it. But let's just bring up something else. trying to remember if these were handwritten solutions or if they were like solutions out of the solution manual. These are handwritten solutions. So these are my solutions to specific homework problems. It's not going to be, I may assign you problems that are different from these, but these are from the past homework assignments and solutions that I've put out there. I have the solutions to all of the problems in the book electronically. I will not share those with you because I'm not allowed to. But if you come by my office or come by and you stay after class, I have no problem, you know, putting them up here on the projector and letting you look at solutions, as long as you have worked the problem and are stuck on it. I'm not just going to put them up there and then have you like take pictures and go home and then try them. All right? But I just don't want you to feel like you don't have a place to go to get the answers to these things. Any questions? We've already wasted half an hour. No questions? Where's the other stack? No, I guess it's back here. This is 3. You need 3.6. Anyone else need 3.6? Just, and everyone here has 3.5. All right. Well, I don't think there's much more to talk about. Y'all ready to get going here? So is Cal 2 more difficult than Cal 1? What have y'all heard? Y'all heard it's harder? I have yet to meet someone who's told me Cal 2 is easier than Cal 1. I have never heard that. Unless they took someone for Cal 2 that was really easy, kind of gave them the grade, I guess. Usually Cal 2 is a much more difficult course than Cal 1. And why is that? Because we're doing everything backwards in Cal 2. It's all the derivatives you did in Cal 1, it's all backwards now. So you have to start with the derivative and go back to where it came from. That's the beginning of the class. And then you get applications which are very visual. That can become a bit of a challenge. And then series, which is completely new to most people, and that usually is a pretty big hurdle. So just be prepared for the challenge, okay? I mean, you can do well. My Cal 2 classes, usually the ones who stick it out past exam 2 do well. But just be prepared for the amount of work you're going to have. All right, let's do the notes. So I'm using Mathematica. Anyone familiar with Mathematica? It's a program, Wolfram Alpha. Anyone ever heard of Wolfram Alpha? Okay. Wolfram Alpha is a website that you can go to get answers to everything, right? This is the actual, what they call the kernel. This is the brains of Wolfram Alpha is Mathematica. So Wolfram makes this math program called Mathematica, and that's the Wolfram Alpha is just a web version of this program. So this is what I use to make my notes, to do all my visual animations and visual stuff. So I'll be opening this, and this is where your notes come from. So what are we, 3.5? Okay, so that's what you're looking at. So I'm just going to work through this. The idea is that we don't have to write all this down, okay, waste time like that. That way we can try and get to actually doing some problems. Ugh. All right, so one-to-one functions. All right, remember one-to-one function? Visual idea behind a one-to-one function is a function that passes both the vertical and horizontal line test. So for every input, there's exactly one output, and each output comes from exactly one place. So you can't have a function like the function f of x equals x squared would take 2 and negative 2 to the same place. So that would not be a one-to-one function, right? 2 would get squared, become 4, negative 2 squared would become 4. So that's not one-to-one. So that's a parabola, and we know it fails a horizontal line test. So just quickly, just as a reminder, you know, remember what one-to-one functions look like. They pass both those tests. If a function is one-to-one, then it must have an inverse, right? If a function is one-to-one, there must be some function that takes it back and undoes it. So let's look at some functions that we are familiar with from pre-cal, our trig functions. This is the sine curve. So you'll see in your notes you don't have, you just have one picture. Here I can control the animation. If you're actually interested in being able to control the animation at home, I can give you these files, and so you can control them at home, but then you have to download this free player from Wolfram's website. And if you're like a computer science major and you want to get into like seeing the code behind all this, just get with me. I'm happy to share this. The coding is in C++. Well, a version of C++. This is the code to make that happen. So if you're a computer science, I'm encouraging you. I'm willing to share, but you have to want to see it. Okay, so that's a sine curve. Is it one-to-one? No. Fails the horizontal line test, right? Fails the horizontal line test. Cosine function, very similar to the sine function, not one-to-one either. Tangent function, let me get these other ones out of here. Tangent function one-to-one? No. So all these trig functions, cosecant, right? Not one-to-one, fails horizontal line test. Secant, cotangent, I'll put them all up here. There they all are. The 6 basic trig functions. None of them are one-to-one, which means none of them have inverses, right? But we know, we've heard of, what, arcsine? So how is it that we get around the fact that these are not one-to-one functions? We restrict the domains, right? We restrict the domains. So we take the sine function. Here's our sine function. And what we say is we're going to restrict it. Instead of looking at the entire sine function, let's just look at it between negative pi over 2 and pi over 2, cut the rest of it off, and within that interval between negative pi over 2 and pi over 2, that sine function takes on all of its outputs. In other words, it gets its entire range, -1 all the way to +1. And within that interval, it is one-to-one, passes both the horizontal line test and vertical line test, right? So if I cut it that way, then it would have an inverse on that restriction. Now, could I have done this? Could I have used that instead? That looks like what? From -3 pi over 2. Can you all see it all right? Let me try and go a little bigger. -3 pi over 2 to pi over 2, negative pi over 2. Is that still one-to-one? Yes. Does it cover the whole range? -1 to 1. Does it get everything there? So why not use that instead? Could we? Sure, we could. We could do this one too. In fact, there's infinitely many parts that we could have cut it to get that one-to-one to happen, right? And since there's infinitely many that we could have chosen, we all had to agree on one. So we had to say, look, let's all use the same cut so that we're not all using different domains and ranges. So we all agreed that this is the one that we use first. When you want to try and get sine to be a one-to-one function, you want to cut off and restrict its domain, we all agree negative pi over 2 to pi over 2 is where we're going to do it. So because of that, we can now define an inverse function on that. The inverse function is arcsine. These are the two notations for it. And we agreed that we're restricting the sine function to this interval. And that gives us the property that we need for an inverse. So remember the inverse function. The inverse, right, the arcsine of x equals y means that sine of y equals x. This is an if and only if statement. So if this is true, then that means this is true. If this is true, then that means this is true. And the only restriction we have here is that the y has to come from between negative pi over 2 and pi over 2. So let's get your brains working here a little bit. Let me just give you a quick little example here. No calculators. What's arc sine of root 2 over 2? Okay, so let's try and remember, when you do sine of something, right, I'm going to use theta. If I say that's equal to, let's say, y, the thing that you plug in here, theta, is an angle, right? The thing that gets spit out is a number between -1 and 1. So when you do an inverse sine function, the thing that gets plugged in is a number, and the thing that gets spit out is an angle. Do we agree? Okay, so this root 2 over 2 is a number. I need you to spit out the angle that creates root 2 over 2 when you plug it into sine, if that makes sense. So this question is saying this: sine of what angle, that's the question, is root 2 over 2. That's what that question's saying, right? So where is that happening? Correct. 45 degrees. Now, this is where you have to go back to your pre-cal and try and remember, how is it that you remember your trig functions? Do you visualize them on a unit circle? Do you visualize the graph? That's you. I can't. I use the unit circle. And since it's the first day, I'll just show you how I would do this. I would say, okay, look, remember that on the unit circle, any point here, given an angle, this is a radius 1. This has an x and a y coordinate. The x is always cosine theta. The y is always sine theta. So if we're saying sine of some angle is root 2 over 2, what we're really saying is, where is the y coordinate on the unit circle root 2 over 2? Where does it happen? 45 degrees. Or in radians, that's pi over 4. Now, we're going to stick to radians more than we are going to do degrees, but they're the same. Right? But usually we want to put our answers in radians. So pi over 4, is that the only place it happens? No, it happens over here also, right? Go to your unit circle, root 2 over 2, sorry, negative root 2 over 2, root 2 over 2. And then over here at 45 degrees, or pi over 4, it was root 2 over 2, root 2 over 2, right? So the y coordinates on this one and this one are the same. So pi over 4 would have worked. What about that one over there? What's that angle? 3 pi over 4? Could that have been my answer? No. Why not? You're restricted. Your domain's restricted. Why is it restricted? Because we're dealing with an inverse function. So you are not allowed, okay? You are not allowed to look over here. It's off limits. If it was open, you know, if it was there, then you would have two answers, wouldn't you? And that would fail to be a function. So the inverse, right? The inverse, you would have one input and two outputs. That would not be a function. So that's why we're restricted. All right, back to this. This is all pre-cal, so I'm just trying to get your brains working here again. Notation, right? You can see the sine inverse or the arc sine. Those mean exactly the same thing. Here's the graph of the two together. Right, so here's the sine function restricted between negative pi over 2 and pi over 2. Here's the inverse, and what you'll notice is that if you take a point on here, the x and the y coordinates change. So if I go to the sine function, let's go out to pi over 2. What's sine of pi over 2? So pi over 2 sine y coordinate is 1, right? If I take 1 and I plug it into the blue function, it spits out pi over 2. So they interchange. How is the function and its inverse related visually? There's a property, if you graph a function and its inverse together on the same xy axes, what's the visual connection between the two? Anyone remember? Reflected over the identity, y equals x. If you imagine a line that comes down here, y equals x, Where's my other program? There it is. Imagine a line that comes down diagonally, like this. That's y equals x. Sorry, it's in yellow. That's the identity. We call that the identity function. If you look at these two and you reflect it, so turn your head and mirror it over, they're mirror images of each other. Every function and its inverse looks like that. All right. Let's just do these quickly. What's arc sine of 1? Pi over 2, right? You're saying where on the unit circle is the y coordinate 1? Pi over 2. How about root 3 over 2? Pi over 3. Pi over 2? So for this one, I'm going to the unit circle. I'm saying where's the y coordinate 1? Up here. That's pi, and that's happening at what angle? Pi over 2. Right? The angle that gets you there, pi over 2. This one, I'm saying where's the y coordinate? Root 3 over 2. And that happens up here. Right? 1/2 root 3 over 2. And what's the angle here? We said pi over 3. Understand? Okay, inverse trig function. So we can do the exact same thing with the cosine function. We can restrict its domain and create a one-to-one relationship and then be able to come up with the inverse. So, but the restriction's different. What's the restriction on cosine? 0 to pi. So let's go back up to this picture that we had here of cosine. Let's get all this mess out of here. What we decide to do with cosine is instead of going, well, why can't we go from negative pi over 2 to pi over 2 on cosine? Why can we not do that? Horizontal. So it still wouldn't be one-to-one that way, right? Because cosine shifted over, it's not going to work like sine does. So we have to pick an interval that will get us the whole range, negative 1 to 1, but then still maintains the 1-to-1 horizontal line test feature that we want. So we go from 0 to pi. 0 here to pi here. We cut it there, then we are good to go. So that's why we say here, here's the relationship, the inverse, where the y has to be between 0 and pi. We can do the same thing with tangent. We can create an arctangent function. We have to restrict that between negative pi over 2 and pi over 2. So I'll let you go back and investigate the tangent. And again, this is pre-cal, so I'm just assuming you've seen this. The remaining trig function inverses can be found in the book, but aren't used much. All right, so you go through the book, look through, go to the index, look at inverse trig functions. You can go look them all up, see what their domain restrictions are. I just expect that you're familiar with these, that you've used them before. All right, we have a cancellation property of inverses. If you take a function like sine and compose it with its inverse, they should undo each other, right? So sine of the arc sine of x should be x whenever x is between negative 1 and 1. And arc sine of x should also be equal to x when x is between negative pi over 2 and pi over 2. So let's do an example of this. Sine of arc sine of 1. What should that be? Should be 1. Now, let's go a little slower here. What's arc sine of 1? We just did that a minute ago. That was pi over 2. So this is really saying sine of pi over 2. But what's sine of pi over 2? So you go to pi over 2, you look at the y-coordinate, it's 1. So it makes sense that that would work, right? All right, compare that to this. What should that be? Pi over 6. Because, well, the cancellation property, but again, let's think about this a little deeper. What's sine of pi over 6? So go to your unit circle, go to pi over 6, look at the y-coordinate. What is the y-coordinate there? 1/2. So arc sine of 1/2. And now you're asking the opposite question. Where on the unit circle is your y-coordinate 1/2? Pi over 6. So that seems like, well, what's the big freaking deal, man? Just cancel. Who cares? Because what about this? Ooh. What's that? It's not 7 pi over 4? I thought the cancellation property said that that's 7 pi over 4. That's right. The restriction, look, the cancellation property says this is fine. We're looking at this one right here. That's always going to work as long as the angle I'm picking is between negative pi over 2 and pi over 2. If the angle's not between there, this cancellation property does not work that way. So when I go back over here and I say, look, 7 pi over 4, that's outside of that restriction. So I have to actually go through and think about this. What is sine of pi over 4, or sine of 7 pi over 4? So you go to your unit circle. Where's 7 pi over 4? That's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. That's where I am, right? And I'm looking at which coordinate? The y. What's the y coordinate here? Negative root 2 over 2, right? Everyone agree with that? So this is arc sine of what? Negative root 2 over 2, right? That's what this was. This was negative root 2 over 2. Now, start over. What angle on the unit circle gives you this y-coordinate, but you're restricted here to here? What's the angle? Negative pi over 4. So you can't come all the way around to it. The only way to get to it is go backwards. So your angle to get down to here is negative pi over 4. That make sense, everyone? Anyone have a question? The moral of the story here is just be careful with the cancellation property, because it's not as simple as just everything goes away except what was there. You have to pay attention a little bit to what's in there. Last one. What is sine of arc sine of pi? Can't do it. Can't do it. Because this is saying here, right, this part right here is saying, what angle, right, do I go to get a y-coordinate, because we're dealing with sine, of what? A y-coordinate of what? Pi. Well, on your unit circle, what's the largest y-coordinate you could possibly get? Right up here, 1, right? It's impossible to get pi out. Pi is bigger than 1. This is totally undefined. You cannot do this, right? Undefined. So you could not just use the cancellation property there and say, oh, the answer is pi. So understand? You got to be careful. Now, if the number here is between -1 and 1, it's just going to spit out the answer, and you're done. Okay, but that's not what this is all about. This is, this is about knowing what the derivatives of these are, right? Cal 1 was derivatives. So I'm sure you probably have seen what the derivatives of the trig functions are, right? Sine, derivative of sine is, derivative of sine is, no, sine. Derivative of sine of x, cosine x. Let it go. Derivative of cosine x is negative sine x. Derivative of tangent x is secant squared x. Derivative of secant x, secant x tangent x. Derivative of cosecant x, negative cosecant x cotangent x. Derivative of cotangent x, negative cosecant squared x. You got to know those first three. The other three, maybe it's been a while. But now, the inverse trig functions is what we want to know the derivative of. So what is the derivative of the arcsine of x? Right? I mean, it's a graph, right? It's a function. So we should be able to define the slope of the tangent line because that's what the derivative is, right? The slope of a tangent line. So what is its derivative? Do you remember how you figured out what the derivative of sine of x was in a Cal 1 class? Do you remember this? The derivative of a function is the limit as h goes to 0 of f of x plus h minus f of x over h. That's the limit definition of the derivative. And so when you're trying to find what the derivative of sine of x was, we replaced all the functions with sine. So this became limit h went to 0. This was sine of x plus h minus sine of x all over h. Then you had to figure out what this went to. And if you were shown this, which I'm sure most of you were shown, you use the sum property of sine. You could split this up into like sine x cosine h plus sine h cosine. Remember that? Maybe not. And then you split the limits up, and then at the end you would get cosine of x would be your answer. I'm not going to go through it again. I'm just trying to remind you how you figured out in a Cal 1 class that the derivative of sine of x was cosine x. You had to use the limit definition to do it. Then once you establish that, you do the same thing for cosine. And then for tangent, you could do sine over cosine, use quotient rule, and then so on and so forth. What I'm trying to get at is how in the hell are we going to find out what the derivative of an inverse trig function is? Do we want to set up a limit and do it that way? Maybe, but you probably could do it. It would be more work than I think we want to do. So before we actually do it and figure out what the derivative of arcsine is, I want to remind you of a couple of things that we had in Cal 1 that you need and you will need throughout the rest of the class. And that is the use of reference triangles and the use of implicit differentiation. All right, so we're going to rely on this heavily right now in order to figure out what the derivative of sine x, arcsine x is. Everyone understand what we're trying to do? Yes? Okay. If y is arcsine of x, find the derivative. We're going to do that. Y is equal to arcsine x. We want to find y prime. So what I'm going to do is I'm going to utilize from Cal 1 implicit differentiation. Implicit differentiation means you take the derivative of both sides of the equation. You can take the derivative on both sides of the equation with respect to x or with respect to y. It's up to you. Or with respect to t. Doesn't matter what you do it with respect to. For us, we're going to do it with respect to x because the derivative of y with respect to x is y prime. That's what we're looking for. So I'm going to remember that this means dy dx. And so that forces me to take the derivative with respect to x. So take the derivative. In my Cal 1 classes, I like to do something to let people know I'm taking the derivative implicitly. Like, instead of just going from this line and taking the derivative without letting you know what I did, I put a wavy line under it. Like, oh, wow, that didn't work out too well. I just do that, and that just lets you know that from here to here, I'm doing implicit differentiation. So what is the derivative of y with respect to y? Y prime, right? Equals, now, the derivative of the right side. That's what we're here for, right? I mean, that's what we want to know. So how am I going to answer? If I don't know what that is, how am I going to do it? So implicit differentiation by itself is useless to us right now, right? Would you agree? So we have to use something else, and that's where I alluded to it right here. We also need this use of reference triangles. So let's see how I'm going to utilize that here. Since I know this takes me nowhere, I'm going to bring this thing down here, and I'm going to utilize the property of a sine and its inverse. I'm going to take sine on both sides of this equation. Now, when I say take sine, I mean I'm applying the function to both sides, right? I do not mean I'm multiplying by sin, right? That doesn't make any sense, right? I'm taking the sine on both sides. Now, what happens on the right side? This should become x as long as what? Yeah, I need to realize that the only way I can say that this turns into x is if the thing in here is what? Between negative pi over 2 and pi over 2, right? So I'm going to put that on the side. You know, if negative pi over 2 is less than or equal to x less than or equal to pi over 2. See, this property won't work if that's not true. So I'm assuming if this is true, then I can continue. Now, on the left side, I just have sine y. And now, let's try again. What is the derivative of sine of y with respect to x? What's the derivative of sine y with respect to x? We're assuming that y is a function of x here. Okay. What is the derivative of sine of anything? Cosine of that, right? As long as this is not a constant. If that was like sine of 2 or something like that, then it would be 0 because that would be a constant. But the derivative of sine of a function is cosine of that function times the derivative of what's inside the sine. What is the derivative of y? Y prime. Or dy dx, however you want to write it. That's called the what? Taking derivative of that, we just use the what? Chain rule. That was chain rule, right? Derivative of sine of y is cosine y times y prime. Now, what about the right side? What is the derivative of x with respect to with respect to x? I just gave it away. 1, right? Derivative of x with respect to x is 1. Well, look at this. I have y prime now, don't I? To get it by itself, I just need to divide both sides by cosine y. So your answer so far is 1 over cosine y. So let's go back up here. We had y was equal to sine inverse of x. And we said y prime we didn't know. We did this little thing using the inverse, or using the cancellation property, and we got an answer that y prime is equal to 1 over cosine y. The problem with that answer is that you're Your right side is in terms of y. It'd be better if it was in terms of x, because your original equation was in terms of x. So I need to figure out if there's a way I can rewrite this to make it look a little better with x's in it. So here's where the reference triangle comes in. Any questions, though, up to this point? Reference triangle time? I'm going to draw a right triangle. I'm going to use this equation, which was the equation that I had before I took the derivative, and I'm going to use that equation to construct this triangle. Y is the angle, isn't it? Because sine of an angle, y must be the angle here. So I'm going to replace or insert this angle y here. And by saying that sine of y equals x, remember the sine was which side over which side? Opposite over hypotenuse. So when I'm saying sine of y equals x, I'm really saying sine of y equals x over 1. I could call x the opposite side and 1 the hypotenuse, couldn't I? So I label this side x and this side 1. And then that right triangle is a visual representation of this equation, isn't it? And what is it that I'm interested in? What cosine of y is? Well, cosine of y is the adjacent side over the hypotenuse. Yes? So you see how I'm going to use this information to be able to recover what cosine y is? Now, I need to be able to solve this side of the right triangle, which I have. Let me separate this so this is its own thing here. I have two sides of a right triangle. That's all I need to solve for the third, right? So what is this side going to be? 1 minus x squared, close, square root. A squared plus b squared is c squared. If you solve that equation, you should be able to get this for this side. If you don't know what I did there, just put a little star and I can talk to you about it later. So what is cosine y? This right here divided by 1. Yes? So what is y prime? 1 over cosine y, which is square root 1 minus x squared. There it is. Does that make sense? No questions? All right, your first group quiz is right now. And what I'd like for you to do is, remember I said I'm going to try and break up the monotony? I'll break it up with quizzes. How about that? That sound fun? It's a group quiz. Come on. You're going to do fine. Here's what I'd like for you to do. Everyone do their own. So you turn in your own, but you can talk to each other, help each other out. You can use your notes. I don't care what you do. If y equals arctangent of x, find y prime. All right, let me pause my video real quick. All right, we're going to move on to the second set of notes. Now, this set of notes is not as long as the ones we just did. So here's where we are right now. We have sine x, cosine x, tan x, secant, cosecant, cotangent, right? Our 6 basic trig functions from pre-cal. In Cal 1, we learned the 6 derivatives of those, right? And then we have the 6 inverse trig functions, which we just talked about, and then the derivatives of those 6 inverse trig functions. So we have each of these inverse. So far, we have how many trig functions? So far? 12 trig functions and 12 derivatives, right? A derivative for each one of these, right? 12 trig functions, 12 derivatives. There's another classification of functions that are not trig functions, but people get them confused with trig functions. There are hyperbolic functions, and that's what this section is about, the hyperbolic functions. So we have, first we have to define what the hyperbolic functions are. Hey, that worked. All right, so the six additional trig functions, which come from, they come from very special combinations of e to the x and e to the negative x. These are called our hyperbolic trig functions. So when we say like sine x, how do you define what sine x is? Like, what is sine x? It's, we know what it looks like, but how do you define it? It's like the opposite side over the hypotenuse on a triangle, or it's the y coordinate on the unit circle, right? Or something like that. I mean, it's kind of difficult to define what the sine function is. When it comes to the hyperbolic sine function, or sine hyperbolic of x, it's very simple to define. It is e to the x minus e to the negative x over 2. That's its definition. Now, we all know what e to the x is, right? Exponential function. So this is just some combination of 2 exponential functions, e to the x and e to the negative x. You could write it like this. Sine hyperbolic x equals e to the x over 2 minus e to the negative x over 2. You could split it into 2, right? If you wanted to. You could write it this way. 1/2 e to the x minus 1/2 e to the negative x. I'm just pointing out the different ways you could write the hyperbolic sine function. All you need to know is that it's a combination of 2 exponential functions, e to the x and e to the negative x. Then you have the cosine hyperbolic function, which is e to the x plus e to the negative x over 2. So very much the same, right? The only difference is this one has a minus in the middle, this one has a plus. And then what's tangent hyperbolic? Well, it's the ratio of the sine hyperbolic over the cosine hyperbolic. So same thing you would expect from in the definition of tangent. What's cosecant hyperbolic of x? Well, reciprocal of the sine hyperbolic. What's secant hyperbolic x? Well, reciprocal of the cosine hyperbolic. Cotangent hyperbolic x? Reciprocal of tangent. So everything else is pretty much what you would expect. It's the actual definition of sine hyperbolic and cosine hyperbolic, which are different than sine and cosine. So if we have now 6 new trig functions, the hyperbolic ones, you know, we're probably going to be interested in knowing what their graphs look like, if they have inverses, what the derivatives of them are, what the derivatives of their inverses are. So let's first take a look at the graphs. That's sine hyperbolic. What do you think about it? Does it look like sine? Doesn't look like a sine function, does it? Does it look like it's one-to-one? Yes. So we don't even have to worry about an inverse on this one. Restriction. We should be able to find an inverse of a hyperbolic without having to restrict any domain at all. So that's what you get when you take 1/2 e to the x and you subtract from it 1/2 e to the negative x. You get that graph. Now let's look at cosine hyperbolic. What does that look like? Looks kind of like a parabola, doesn't it? Is that a one-to-one function? No. So we would have some issues trying to come up with an inverse for that one. Now that is not a parabola though, all right? It is not a parabola. It looks kind of like one, but it's not. And anybody know? Well, I'll show you later, not now. Let's look at tangent hyperbolic. Does that look one-to-one? It looks like it, right? These look like we have asymptotes, horizontal asymptotes. Looks like it, right? But it still looks one-to-one. Here's cosine hyperbolic. We actually have a problem here, don't we? We have an asymptote, vertical asymptote at 0. The function is undefined at 0. Secant hyperbolic looks like this. And cotangent hyperbolic looks like that. The main reason for me showing you these is just to show you that, you know, with sine and cosine, they looked very much the same, right? They were just shifted. But with the hyperbolics, they all look very different. So it's a whole different breed of functions, and they come up a lot. So let's show now that cosine hyperbolic squared of x minus sine hyperbolic squared of x equals 1. What identity does that look like from pre-cal? Sine squared x plus cosine squared x equals 1, right? But it was a plus between them. For the hyperbolics, it's a minus and the cosine goes first. Let's show that that's true. So what is cosine hyperbolic squared x? What is it? By definition, it is e to the x plus e to the negative x over 2 squared. That's what this is. Yep, Cal 2? Yes. No, it's all right. I was just about to let everyone go for the day. No, I'm kidding. What's your last name? Yep, you're on here. Okay, so we have, so you were like over an hour early then, in your mind? Yeah. Okay, all right. Okay, the e to the x minus e to the negative x. Do you want to be in this class this early? I mean, I think there's one that starts at 12:30. Okay. 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 So this is the hyperbolic cosine squared here minus this. We need to show that it's equal to 1. We don't write equals 1 because we don't know that. We're trying to verify that. So we have to square this. Square this, and it should come out to be 1. Let's see. So when we square this left one here, we have to multiply out the top. Let me write it down a little slow. Like this. This is what it means to square the top, right? Multiply times itself. On the bottom 2 squared is 4, right? And then I'm going to say minus, now let's do the same thing on the other one. We're going to take e to the x minus e to the negative x times itself, e to the x minus e to the negative x, then over 4 again. This is just an exercise in messing around with some algebra and the way that e's go together. On the first rational expression, let's distribute or FOIL or expand. Let's do this. So what is e to the x times e to the x? E to the x times e to the x. E to the x times e to the x is e to the 2x. You have the same base, you add the exponents. E to the 2x. That was this multiplication right here. What's this multiplication? What's e to the x times e to the negative x? E to the 0. What's e to the 0? 1. Right? Any number to the 0 is 1 except 0 to the 0, which is undefined. So that second multiplication through, that green one there, is going to give us e to the 0, which is 1. Follow? Is it plus or minus? Plus. So plus 1. Okay, do the middle multiplication, which is this one. The pink one there. E to the negative x times e to the x again. It's going to be 1 again. And then finally, come out of colors here. Oh, there we go, yellow. What's that? It's e to the negative x times e to the negative x. E to the negative 2x. Right, because you're adding the exponents again. Negative x plus negative x is negative 2x. All of this over 4. All right, same thing on the other one. So I have minus, now let's do the top here. E to the x times e to the x is e to the 2x. The next one will give me a what? E to the x times e to the negative x. It'll be negative 1 this time because there was a minus between. So minus 1, the next one will be these two, which will give me another minus 1. And then the last two together give me a positive e to the negative 2x all over 4. So that's the exact same thing, but you have to be careful with the signs. And now, since they both have a denominator of 4, we can put them together, right? And we have to be careful to pass this negative sign distributed through to each of those terms. And that'll change signs, and we should get this to work out nice. E to the 2x plus 2 plus e to the negative 2x minus e to the 2x plus 2 minus e to the negative 2x all over 4. And now what happens? Bunch of canceling, right? 4 over 4. So that's your, it's not a Pythagorean identity because it's not using a right triangle, but this is the identity, one of the identities for your hyperbolic trig functions. Cosine hyperbolic of x squared minus sine hyperbolic of x squared equals 1. And that's how you verify it. Questions? There are a bunch of identities, as you might suspect. I mean, remember, in pre-cal, you had a bunch of identities for the trig functions, right? There's a bunch more for the hyperbolics. Here are a few. These are the important ones. What is this? This is a property. Do you remember that property? If you plug in negative x into the hyperbolic function, sine function, it's the same as plugging in x, but then making it negative. Do you remember what that's called? Even odd. Remember the even odd properties? Even odd? No? That would mean that that is a what function? Even or odd? If f of negative x equals negative f of x versus f of negative x equals f of x. One of these is even, one of them is odd. Which one is it? No? It's been too long, huh? This says that if you plug negative 2 into a function, it's the same as plugging in 2. What function does that? How about x squared, right? X squared, you plug in 2, it's the same as plugging in negative 2. X squared 2, like power 2, even. Even functions behave this way. Odd functions behave this way. So take like x cubed. That's an odd function, odd power. What happens if you plug negative 2 into x cubed? What do you get? Negative 8. So that negative 8 should be equal to the same as if you plugged in 2. What's 2 into x cubed? 8, but then make it negative. Negative 8. So odd, even. This is an odd function. This is, cosine hyperbolic is a even function. This is the identity we just verified. What is this? It's this identity dividing each term by cosine hyperbolic x squared. Divide this by cosine hyperbolic x squared, what do you get? 1. Divide this by cosine hyperbolic x squared, and you get what? Tangent hyperbolic x squared. Divide 1 by cosine hyperbolic x squared, and you get secant hyperbolic x squared. So that's just an application of manipulating the identity we showed. Some formula for hyperbolic, for sine and cosine. All right, so that's what they are. That's the way they behave. That's their properties. But we just want to know derivatives. So I think what I'll do is I'm going to show this first one. Or you know what? I'm not. I'm going to show this one. I want to show you that the derivative of the cosine hyperbolic function is sine hyperbolic, not negative sine hyperbolic. Okay, let's see if we can show this at all. All right, so this means the derivative. What is cosine hyperbolic? Give it to me in terms of the e stuff. E to the x plus e to the negative x over 2. Let's take the derivative of that. Well, how about before I take the derivative, I split it up. Remember I said there was different ways you could write it? That's the same thing? Same exact thing? I have not taken a derivative. But now take derivative. It's 2 different terms. What is the derivative of 1/2 e to the x? 1/2 e to the x, right? Same exact thing. Derivative of e to the x is itself. So you have the 1/2 in front, e to the x. Plus, now, derivative of 1/2 e to the x, I write 1/2 again. Sorry, e to the negative x. Derivative of e to the negative x is itself, all right? E to the negative x, but then what? Times -1, which is the derivative of what was up here. Derivative of negative x is -1. So it pops a -1 out, and that changes the problem into 1/2 e to the x minus 1/2 e to the negative x. See how that -1 has the effect of changing that plus to a minus here? And then if we put those back together into a single fraction, what is it? That's sine, hyperbolic. So it does not behave the way the regular trig functions do, right? Regular trig functions, derivative of sine x is cosine x, derivative of cosine x is negative sine x. But with the hyperbolics, not the case. So that's what these are. These are the 6 derivatives. They're pretty similar to the ones we've seen, right? There's some sign issues that aren't the same, but derivative of tangent x is secant squared x. Derivative of tangent hyperbolic x is secant hyperbolic squared x. So that there's some connection. So if you have now new derivatives, then you should be able to apply these. So do this one on your own. See if you can get this one real quick. Find the derivative of that. You have the notes, right? So you can see what the derivatives are on your sheet. Do you need a set of notes? We did 3.5. We're on 3.6. Okay. Whoa. I'm just going to give you a few minutes. I don't want you to help each other on this. I just want to see what you can do. Okay, I've put the solution up here. Product rule? Is that what you're talking about? So you should have a product rule happening here. Product between x and secant hyperbolic of e to the x. So the derivative will be the derivative of the first one, which is 1, times the second one, which is this. So done with the first part of the product rule, plus the derivative of secant hyperbolic of something, is, according to the formula, is what? Negative secant hyperbolic of that something times tangent hyperbolic of that something. Chain rule. Go inside. What's derivative of e to the x? E to the x. And then the x on the end is finishing off the product rule. Then I noticed that these both, this is like a term here and a big term here. And so I factored out a secant hyperbolic of e to the x from both terms, which left a 1 here and left all this other crap over here. That's it. Questions? Okay. All right. Now, if we now have 6 new hyperbolic trig functions and 6 new derivatives, then we talked about we could find inverses and have 6 more trig functions, the inverse hyperbolic functions. So here are the inverse hyperbolic functions. There's 3 of them. The rest of them are in the book. These don't come up very often. Okay, we're not going to use them a whole lot. I just want you to know they're there. So here is secant hyperbolic inverse of x. It's equal to natural log of x plus the square root of x squared plus 1. What? So this is a great opportunity to show you something. Now, this is not a derivative, right? It's the definition of the inverse hyperbolic function, the inverse sine. Do you all remember how you can find the inverse of a function? Somebody gives you a function, how to find its inverse? Like, for example, if someone says, hey, f of x is 3x plus 1, what's its inverse? Do you remember doing this? You know, y equals 3x plus 1, and then switch x and y, so replace like this, and then solve for y. Divide both sides by 3. This is your inverse function. So you replace f of x with y, you swap the positions of x and y, you solve for y, that's your inverse. Yes? That's college algebra very, very long time ago. Can you prove that this is the inverse of the hyperbolic sine function? Let's show it's true. This is a great exercise, all right? So we're about to do it. We want to show this. Here we go. The only information that I can use to show that is starting off with the fact that sine hyperbolic x is defined to be e to the x minus e to the negative x over 2, right? That's what I can start with. That's the definition. I need to find the inverse of that function, don't I? I'm trying to find the inverse and show that it's the natural log of all that junk. So this is really like my f of x. So let's replace f of x with y. Now what did we do? Switched x and y, switched their places. And then what? Solve for y. Uh-oh. Solve for y. So you go to Wolfram Alpha. You type in solve for y, right? No. How in the hell are we going to solve that for y? It's going to involve a natural log, but when? I can't do natural log now. Okay? So I want you to help guide me through this, all right? This is, like I said, is a great example because we're going to do some algebra in here you may not have ever used before, or maybe it's been a long time. 2x, or maybe you've used it, and I'm not going to impress you at all. Okay, I agree with that. Multiplied by 2, both sides. Yay. Now what? Do you see the problem with trying to come in with natural log now? If you try natural log now, because why natural log? Because natural log is the inverse of e, right? Natural log will kill off e. But if you try it, don't write this down. If you try it, you cannot do anything to this on the right side. You can't split that into 2, do anything like that. Because properties of logs don't allow you. You can do this with logs. If you have a product inside of a log, you can split it into 2 logs. But if you have a sum or a difference inside of a log, you cannot split it to 2. So we are stuck if you try that. Do y'all understand? So, sorry. No go. Trying to isolate y. All right. So I think this is a good opportunity. Let's take out your polling devices. Is there an extra one over there? You need one? Just one? There's an extra one? Okay. This is an anonymous poll. So what I want to know, looking at the equation right there, is whether or not you know what to do with that. Yes or no? Do you know how to solve that? Without a computer or calculator. All right. Okay, we done? I was expecting it to be something like that. So do any of my 12 percenters want to guide me through this then? You want to make the e to the negative y of 1 over e to the y? You can do that? Yes? Okay, so let me try this. 2 e to the x. So this is 1 over e to the y. That's what you're saying? Everyone okay with that? Now what? You want, if you're taking natural log on the left and right hand sides right now, you still can't pass the log to both of these. It would be the log of the entire side, and those can't be split yet. So you're not, natural log cannot come in quite yet. It's going to come in, but it just can't come in yet. Do you understand what I'm saying? Why it can't? You know, common denominator. Everyone agree you could do that? I'm not saying this is wrong. I'm not saying it's right, but it's good algebra. Common denominator. You want to do just this side or both sides? Just this side. Okay. So over here, common denominator. So this is like a 1 over here on the bottom. So I'd have to introduce an e to the y on the bottom here, wouldn't I? Which means I have to introduce one on the top. So e to the y multiplied top and bottom would give you what? On the top, it would be e to the 2y, and then minus 1 over e to the y. That would be common. That's all good algebra, okay? Nothing is wrong with this. Everything's good. I agree. Now what? You could do the division. If you did natural log right now, because you have division, you could split it into 2. The problem will be that the top one can't be split, right? The e to the 2y minus 1 still can't be split. So this is, this is a great problem because it's solvable. You may not have ever seen how to solve this before, but you have to have a mentality in this class, especially in Cal 2, of you're going to fail more than you're going to succeed, okay? When it comes to homework and trying problems, you're going to fall a lot of times. You have to get up and keep going. And it's whether or not you're willing to take a swing at it or not. How many swings are you willing to take? You've got to take a swing at this. You've got to try something. And a lot of that's like the theme of this class. You're sitting there with a problem, you're stuck, you've got to try something. It's kind of like a real life, right? Real life, you want to be an engineer or something like that. You're working with a group of people, you have a problem, you're trying to solve it. You're either the type of person who is going to try something and keep trying until you figure it out, or you're going to sit there and go, I don't know. Right? They want the problem solvers. They want those people. That's what we're looking for, right? That's what you want to become. Maybe it's not interesting because it's just an algebra problem, but did y'all see they had like a robot competition the other day? Did you see that? Pretty cool. So I don't know. I didn't watch the whole thing, but I saw a robot driving like one of those like not a golf cart, the souped up golf carts. What are those called? What? Polaris. Like driving a Polaris. Robot gets out and like goes and like cuts a hole in sheetrock with a sawzall and like doing all this stuff. Like holy shit! Pretty soon that'll be someone up here like this. Welcome to calculus 2. All right, so come on. Someone take a swing. You got to do something. I'll tell you if it's legal or not. Someone take a swing. Can't be afraid to be wrong. That's where we just came from, though. So if you want to go back, we could. That would be legal. But we'd be back where we were. All right, I'm glad you said that. Implicit differentiation. What is our goal here? Our goal is to just solve for y, right? If we take a derivative, we're introducing something completely different, right? So you could, but is that going to get us closer to getting y by itself? It's going to introduce derivatives of y, and then we're going to be even probably further away from where we want it. So yes, you could, but is it going to help us? So algebra here. You don't like fractions? Nobody likes fractions. Can you make that not a fraction on the right side? Multiply both sides by e to the y. Is that a legal move? Okay. 2x e to the y equals e to the 2y minus 1. Now I can already kind of sense that people are feeling like maybe we can get that e to the 2y by itself right now. But the other side is going to have an e to the y also. We want y by itself. It's never okay to solve for a variable in terms of itself. Then it's not truly solved. All right. Can't take too much more time on this. What I was trying to get at here was really seeing how many people do we want to revote? How many of you know how to solve this? Yes or no? I'm still looking for my 12%. Okay, it's dropping. All right. All right, so we will concede as a class. Everyone is conceded. All right. You have to humble yourself and make sure you're okay with that. All right? So now I show you. And then once you've seen it that first time, then you don't forget it. You always have that in your arsenal of a way to attack a problem. So here it goes. All right? I'm going to move everything to one side. All right? So here it goes. E to the 2y minus 2x e to the y minus 1 equals 0. So I moved everything to the right side, but then I just put the 0 on the other side. Now, does anybody see it yet? Factor out of what? E to the y. But we'll still have an e to the y there. Let me just show you what would happen. If you pull an e to the y out, you'd have an e to the y minus 2x minus 1 equals 0, right? So you'd still have an e to the y here. You cannot move one to the other side and set them both equal to 1. Right? You cannot do that. Do what? Quadratic. Yes. How, though? How is this a quadratic? This is the big light bulb part right here. I'm going to make a substitution. U is equal to e to the y. What is e to the 2y? E to the 2y is the same as e to the y squared, isn't it? Because e to the y squared, you multiply these two, and y times 2 is 2y. So I get u squared there. U squared minus what? 2xu minus 1 equals 0, right? Now this is crazy because you've seen quadratics before. But quadratics have always had one variable in them, right? Like it's been a quadratic in x or a quadratic in y or a quadratic in some variable, m, n, whatever it is. You actually have a quadratic here in two variables. But I'm going to treat the number in front of u squared as my a. Remember that was our a, right? ax squared plus bx plus c equals 0. I'm using this. Right? But instead of x, I'm using what variable? U. What is a for me in this problem? 1. What is b for me in this problem? Negative 2x. And what is c? Negative 1. Do y'all see that? In that formula. A is negative 1, b is negative 2x, and c is negative 1. See, normally when we use a quadratic formula, we get two number answers usually, right? Sometimes there's one answer and sometimes there's imaginary answers. But a quadratic formula usually gives us numerical answers. Because we have two variables here, our answers are actually going to be in terms of the other variable. That's okay though. Let's see what happens. Using the quadratic formula, QF, we get what? U is equal to, what's the quadratic formula? Negative b plus or minus, all that stuff. So what's negative b for us? 2x. Plus or minus the square root. What's b squared? What's b squared? 4x squared minus 4 times a times c. 4 times a times c, so plus 4 all over 2 times a, which is 2. Let me just clean that up. Do I have any questions on where I got that? That's quadratic formula applied to that. Can I pull a 4 out inside the parentheses? I mean, inside the root. Factor 4 out and then pull the 4 out of the root and it becomes a what outside? 2 and then reduce everything by 2? So you get x plus or minus square root x squared plus 1 all over 1. So this is it. This is what u is. Are we done? No, what was u? We came in, we introduced u, didn't we? What was u? E to the y. So e to the y equals this, doesn't it? I'm going to go to a new page. So e to the y equals that. And now you can get the y out by doing what? Natural log on both sides. So take the natural log of the left side. Take the natural log of the right side. And the left side is y equals natural log x plus or minus square root x squared plus 1. Done. Now, that should be our inverse function. Let's go take a look if we're right. It says it's only plus, not plus or minus. I wonder why. Why can't it be minus? What's that? Well, kind of. I mean, tell me about this. Tell me about this right here. That part right there. If I had a minus here. Is x squared, what's the square root of just x squared? Just x squared. If there was not a 1 here, what's the square root of x squared? Just x, right? What's x minus x? 0. Okay. What if I have x squared plus 1 square root? Is that bigger or smaller than x? It's bigger than x. And then you have x minus something bigger than x, which would be a negative number. And then you're trying to take the natural log of a negative number, which is not allowed. Understand? So it cannot be the negative case. It must be the positive. So we chunk it. Just the plus. All right. So that was fun. For me, I don't know about you. You could do the rest the same way. You could do these two, show the same thing. Cosine hyperbolic inverse. Now, we're only looking at 3 of them because the other ones aren't used very much, right? That's what I said. We just showed that. All right. We have about half an hour left. I have not given you any formulas yet, right? For the derivatives of these yet. Let's show that the derivative of the hyperbolic cosine inverse of x is 1 over the square root of x squared minus 1. Let's show it's true. Are you all ready to do it? You have no choice? See if you can help me figuring out what this is. I'm trying to show that that's true. So if I call y equal to the cosine hyperbolic inverse of x, I want to know what y prime is, right? And I want to show it's that. How do you think we're going to do this? I'll give you a hint if you'd like a hint. This is what your quiz, your group little quiz thing was. Same approach, just different type of function. So what did we do in that quiz thing to try and get to work this out? Okay, so take cosine hyperbolic on both sides. Apply it to both sides. When you do that, you get cosine hyperbolic y, and then cosine hyperbolic of cosine hyperbolic inverse of x. The right-hand side should become what? X within the domain restrictions, which we didn't talk about. We're not going to get bogged down in domain restrictions. They're all listed out for us, all right, in the book. We get cosine hyperbolic y equals x. Now what? Why did we do that? Why did we do that? We took the derivative at this point because we knew what the derivative of the left side was. That's why we did it. So we're going to come in here, we're going to take the derivative implicitly. So what is the derivative of cosine hyperbolic y? Sine hyperbolic y times y prime. Good, you have to apply the chain rule. Equals 1. Which means that 1, or y prime equals 1 over sine hyperbolic y. Questions? Are we done? That's what we did last time, right? That's what we did. But that was because we were using trig functions. And trig functions are all based on a right triangle. The hyperbolic trig functions are not based on a triangle. So you have no triangle to go to here. But you need to find a way to represent sine hyperbolic y in terms of x instead. So help me try and get that in terms of x. If we can't do a reference triangle, we got to do something else. What do you know about sine hyperbolic y? What is it equal to? In terms of x, what is it equal to? Or sorry, come back up here. Look at this right here. This is what we want to know, right? Any ideas? How can we use any of this information? This is what we're trying to get it to look like, right? Somehow it turns into this. No? Let me go back to these identities. Will any of these help us? Okay. How do you want to use that third one? You see, the issue we have is that we have a y here, right? Cosine hyperbolic y equals x. I need a relationship between x and y. Solve for y, solve for x here, which we did here, right? We solved for x. I think I've got a stuck class here. I'm trying to decide if I want to offer this as a bonus now. Because I don't see anyone getting it. Or like seeing it right away. Are you saying here? If you wanted to write that in terms of its definition, right? Sine hyperbolic has subtraction, right? I don't know if this is what you're saying or not. Is that the definition of sine hyperbolic of y? I want to know what that is. That's what that is, right? Sine hyperbolic y is this. But I'd like it in terms of x. The identity, where? Here? Okay, so what would this say? What would this be telling us? That e to the y minus e to the negative y, plus, sorry, over 2, that's the left side, right? Equals what? X? Again, I don't know if that's what you're telling me to write. But isn't that what this equation means? Let's offer this as a bonus. I think some of you are starting to get close to it. I'm going to say this is a bonus to be turned in next class. Don't share your answers with people, because if everyone turns in the bonus completed, it's worth less. Okay, so if you can get it, and what we'll do is we'll pick up with this next class. Not next, we're not done, but I will address it. I will show you how that one is finished off. Somehow, you know what the answer is, right? It needs to be this, right? The derivative needs to be this. Somehow, 1 over sine hyperbolic y turns into that. All right. Let's see what else is left in our notes here. The other derivatives, all right, for the other inverse hyperbolic trig functions are in the book, and they're also on your formula sheet. So if you look now on your formula sheet, formulas 13 through 36 are all the derivatives of all the trig stuff. The 6 basic trig functions, the 6 hyperbolic trig functions, the 6 trig functions, the 6 inverse trig functions, the 6 hyperbolic trig functions, and the 6 inverse hyperbolic trig functions. All their derivatives are here. All right. The last little thing, some usefulness for these hyperbolic trig functions. Usually this works pretty good. Let's see if I can do this. Nobody happens to have a string with them, would they? A rope or something? No. You do. You just happen to have a rope. Thank you. Oh, and that's perfect rope, too. I couldn't have asked for better. Yeah, it's okay. So when you take, I don't know. Oh, wait. We'll figure it out. This looks like its own problem here. Oh, there we go. Might get enough. If you take a rope or wire, cable, or something like that, and you hang it between 2 poles, let's say, would you mind? Then just touch the dot there, right? When you hang this now, if I make it shorter, it's going to come up, right? And a little longer, it's going to hang like that. Now, I need another volunteer to hold this side up for me. Go ahead, whoever. Not all at one time, please. Just, yeah, hang tight. Save your energy. So when you hang rope, bring it up, shorten it so we can see the bottom where it's hanging. Keep coming up right about a little more. That's a perfect rope. Okay. So when you hang that, it looks kind of like a parabola, but it's actually not a parabola. There is a function that models that exactly, and it's called a catenary. And what I would have to do is adjust it. Oh, don't mess with that one. You know what? I'm going to leave mine. You let some more rope out until you. All right. Now bring it in a little bit. Oh well. Make sure you're touching the dot, the ends. Yeah, it's kind of I missed. Okay, you see that? That is exactly the way it would hang, and it's not a parabola. It's actually that function up there. You see that function up there? A cosine hyperbolic x over a plus c. So when you look at like utility poles and they have wires hanging, that is called a catenary, and it is a hyperbolic trig function that models that hanging wire. Okay, that's good. Thank you. Man, had the rope. Give it back to the young lady. Thank you. All right, so why is that important? Well, what are some things we did in Cal 1 when we had a function? What were some of the things that we could do in Cal 1? We could find the derivative, right? So let's say that we have, let me take this picture real quick and copy it. Put it in here. Let's say that we have a utility pole, right? Hopefully the wire's not that close to the ground. And a utility pole over here, right? And we have cable there, right? Well, first thing we want to know is how much does that cable weigh, right? Which means we need to know the length of the cable. Can you find the length of a curve? In Cal 1, you could find arc length. Or, no, sorry. Not in Cal 1. In this class, we can find arc length. In the wrong calculus class. So we can actually find the length of that curve. We'll be able to do it later. So we know how long the wire is. If we know how long it is, we know how much it weighs. And then what we could do is we could say, all right, take a look here. Where this comes in, imagine a tangent line coming in there. We know the slope of that tangent line, don't we? That's the derivative. What's the derivative of a cosine hyperbolic function? A sine hyperbolic function. So we could find the slope of that line. That's important because I need to make something that will be able to hold the wire, right? So it doesn't fall. And I need to know the angle so I can know the force being exerted on that bracket. Now, what do they use to hold these wires? If this is an electrical wire, what do they use? Have y'all seen them? They got the wire coming in. Here's like a zoomed in picture of the wire. And then it attaches to this thing. You may have seen them. They look like this. It's a terrible picture. Have you seen those? Look up on a utility pole. See these things? No? Have you ever noticed those? They're ceramic insulators, so electricity can't pass through it and go down the pole. So the wire goes into the ceramic insulator, then it jumps, they put a wire, goes around the pole to another ceramic insulator, and then goes off to the next pole and keeps doing that, right? So you want to know that angle because you want to know whatever that tangent line is right there is the direction in which the force is being exerted on that ceramic insulator. So if your ceramic insulator is not strong enough, right, that's made out of glass or ceramics. It's brittle, right? So you have to make sure that your wire is not going to break that. So you can figure out the force, the exact force being that thing is being subjected to, but you need to know the angle, which means you need to slope a tangent line. So there's just so many different things you can do with it, but you needed to know the function in order to be able to do all this, right? You couldn't just be like, it looks like a parabola. Oh, well, just use a parabola. You got to know the exact function. So
That's just one of these side little things about catenaries, or about hyperbolic trig functions. All right, there's the homework for that. 189, 26 through 41 odds, 47, 48. Pardon me? 26 an odd number today. I don't know why I put 26. Let me see. Yeah, you do 26 if you want. Don't if you don't. 36. Yeah, you can try 26. All right, we've got 15 minutes. You know, I think this is a good place to break. I mean, we could start 15 minutes of new material, but we may as well just start next time. Y'all ready to go? Okay, make sure you do your homework. Things are going to pick up quickly in here. Be ready next time. Have a great day.